Okay, testing 1, 2, 3. Can you all hear my voice? Boleh dengar tak?
Boleh dengar.
Okay. Going to start soon. Only 43? Where is the rest? You're going to start. So we're going to continue chapter 5. We will finish this chapter today because next week we're going to continue with a new chapter. Right, can we start now? Okay, before we discuss on new subtopic, okay, can you recap on what we have learned last week? Anyone? Any volunteer? We learn about flow of energy by mass. Before this, you only learn about energy transfer by heat and work only. But last week, we learned about flow of energy by mass. E by mass, energy transferred by mass. So can you recall what's the expression for energy transferred or transport by mass? Because this expression we were going to use in all the steady state engineering device. So you must remember this. You must memorize this. So E energy transferred by mass is given by M times H plus V square over 2 plus G Z. Right. And if you can also write in terms of rate, right? And this will equal to flow rate, mass flow rate times enthalpy, and then this is the change of kinetic energy plus the change in G. Sorry, this is kinetic, this is potential energy. So this is energy transferred by mass. And we learn about what? We also learn about steady flow operation. Steady flow operation. Right. So in steady flow operation, okay, what is the assumption used for steady flow operation? Mass in equal to mass out. And there is no change in mass. There is no change in mass over time. So dm over dt equal to 0. Same goes to energy. So energy in, sorry, the rate of energy in, this is the rate of mass in, the rate of mass out. Okay, and then this is energy in, rate of energy in equal to the rate of energy out. And for steady flow operation, the change of energy over time will be equal to 0. Right, so this is the important assumption for steady flow operation. Right, and then what is the, can you recall the general energy balance for steady flow operation? Okay, let's write it here. What is in, what is out? So the energy in, the rate of energy in equal to the rate of energy out. And how you derive all the energy in and energy out? So energy in equal to all the heat in plus W in plus, this is energy transferred by heat, this is energy transferred by work, and then plus energy transferred by mass. Yang tadi tu, the previous one, so the energy transport by mass is mH plus V square of 2 plus Gz. This is enthalpy, this is kinetic energy, this is potential energy, and then this is obviously, and then what is rate of energy out? Same expression, but then this is for out lah, and this is Q out, heat transferred by energy transferred by heat, and then energy transferred by work, and energy transferred by mass. So M2 or M out, H plus, this is H2, this is H1, this is V1, this is Z1, and V2 over 2 plus GZ2. So this is, okay, this expression, make sure you memorize this. This is very important and it is not given in the exam. Okay, and okay, if you look here, this is the basic one, the one that I told you to memorize earlier, right? This is what energy in minus energy out equal the change of energy. This is the one that I asked you to memorize. But we are using this from the beginning. And because for steady flow operation, there's no change in energy of the system. So your energy in will be equal to energy out. So that's why we came with this equation, and this is aspiration. This is a full aspiration. Right, and then we learn about what are the steady flow engineering device that we learned last week. We learned about what nozzle and diffuser, right? And then what is nozzle? A device that is used to increase the velocity, while the diffuser is the reverse of nozzle to reduce the velocity. So you have to remember that. Okay, now we're going to this week we're going to proceed with uh, turbine and compressor. All right. So what is turbine? Turbine, as you can see here, turbine drives the electric generator in a steam, gas, or hydroelectric power plant. Okay. Now, as the fluid passes through the work is done. So this is the important part. For turbine, work is done. So yang tadi tu, so work, you know that the expression here, you know that there is work done. So you need to consider, sorry, this is work in, not work done. Work done is work out. Work done is work out. And work done, betul lah, work done is work out. So you know that you cannot neglect or ignore this expression. And then what else? Turbine. Okay, as a result, the shaft rotate and the turbine produce work. So because work is done, turbine produce work. So that you have work out. Work out. Produce work, not requires work. And then for compressor, as well as pump and fan are devices used to increase the pressure. Okay, what's the difference between compressor and turbine? Compressor, pump, fan, and turbine. What the difference between these two? One, this is two. Okay, this device number two is the reverse of turbine. If a turbine produce work, okay, this device requires work. So work is supplied to this device from external source through a rotating shaft. So this is the important point that you need to know lah. You need to memorize this because we are going to use the general energy balance equation. Then you're going to consider this. Okay, and then what else? Okay, now what's the difference between fan, pump, and compressor? So okay, fan is fan used to increase the pressure of gas slightly and is mainly used to mobilize a gas. And then a compressor is capable of compressing the gas to very high pressure. Okay, so what's the difference here between compressor and fan? Compressor can press gas to very high pressure, but this is for fan, it compressed to slightly low pressure, right? Not very high pressure compared compressor. And what is the difference between compressor and pump? So compressor is used for gas, but pump is used for liquid, right? And then so both fan and compressor used for gas. This is for gas, but pump is used for liquid. Okay, so it's very much like compressor, except that they handle liquid instead of gas. But for fan and compressor, they used to compress gas lah, or to transport gas. Same goes to liquid. Yeah, same goes to pump. You want to transport a liquid, so you need this device to increase the pressure. Okay. Now, so we're going to look at the energy balance for these devices. Okay. Now, for compressor first. Okay. Right. It's already written here. Okay, you need to write. Like I mentioned previously, you need to memorize the general energy balance for this device. So, what is the general? What is E in? What is E out? So, E in equal to Q in plus W in plus this is energy transferred by work, and then another term is energy transferred by mass. So mh1 plus v velocity over 2 plus gz 1 equal to out. So this is E in, and then what is E out? E out is sama je the same as the same term as in E in, but then you need to write it as out. Q out, and then work out plus M H2 plus V2 plus G Z2. So you need to remember this. Okay, then only you can remove all the insignificant for compressor. You know that compressor requires work, so there is work in. You cannot ignore this term lah, right? What else? Okay, usually for compressor, the kinetic energy, the change in kinetic energy and the change in potential energy equal to zero because they are very small, so they can be neglected. So if this KE and PE equal to zero, meaning that we can remove this term, leaving okay, so there is, we also know that for compressor you only require work, no work out. You can also neglect this term. And then what else? Usually uh, Q also zero lah. There is no heat transfer. But then it depends on the case. Some case there require there is heat transfer, but usually there is no heat transfer. So you can neglect this Q. So leaving only W in and MH term, right? So but here this is according, because you have Q out here. This is according to the example that we're going to discuss later, right? So can you see why I asked you to memorize the general energy balance equation? Because this is important, because you're going to use the information given by in the question. So you cannot just simply memorize, because we have last week we have two, and then we're going to have like 4 or 5 more. Then you cannot memorize all the 7 energy balance equation. You just memorize the general one, then only you can remove the insignificant term according to the devices that you use, right? So okay, now let's take a look at the example. Right. Now air is at this is pressure 1, this is temperature 1. Now air is compressed, so we know that this is a compressor lah, right? Air is compressed steadily to this P, so this state 2, P2 and T2. Okay, the mass flow rate of air is, this is mass flow rate, 0.02 kg per second. And then heat loss is given, so this is kj per kg. So this is small q. So this is Q out. Kalau if only 16 kg, this is Q. If per unit mass, this is small q, right? And then what else? Assuming the change given in the equation, change in kinetic and potential energy is negligible, so you know that PE and change in KE equal to 0. So first and foremost, you need to write the generals energy balance, Q plus W plus MH M1 H1 plus V square V square, tak dekat. Okay, V square over 2 plus G Z1 1 equal Q plus W ataupun W. Sorry, this is in This is in, this is out. Okay, in equal to out. So this is W out plus Q out plus this is M out, enthalpy out plus V2 over 2 plus VZ2. So from the information, potential and kinetic energy is zero. So you just remove this term. And then we know that for compressor, work done ke work done or work in or work out for compressor. It requires work even in the question, right? Not given. So we know that for compressor we requires work for compressor to operate. So you have work in, but then there is no work out. So you remove work out. And then given that there is Q out, so obviously no Q in, you remove Q in here. So now what's left? So this equation will become only what? W in plus M1H1 Q out plus M2H2. So we're going to use this equation to solve the problem. All right. So can you see what, can you understand so far? And then,
Yes.
yes. And
Uh,
then, yes, yes, Tom.
no, I mean we can understand.
Okay. And then you also must remember the what? The schematic diagram of a compressor. So because this is a compressor, obviously you're going to compress, so the volume will become smaller. Right. So this is a schematic diagram of a compressor. How about turbine? Turbine is the reverse of compressor. So yang terdepan is small and then small to big. So this is turbine, and then we know that for turbine there is work done, or work out lah. For this is turbine, this is compressor. Right. So you, if in the question ask you draw or sketch a schematic diagram of the process. So if this is compressor, you know this is schematic diagram of a compressor, right? And then if turbine, you know this is the turbine schematic diagram, right? Now what's okay? What do you need to calculate? You need to calculate, determine the necessary power input. So you want to know what is your to the compressor. So you're going to calculate what is work in. All right. Okay. So what's the assumption? Obviously, your first assumption should be this. This is a steady flow process. Because why? Because there is a big steady flow. So we assume that there is no change with time for mass and energy. The change of mass and the change of energy for the control volume. Right. And then what else? You assume that because it's air, so you assume this is ideal gas because according to the working operating parameter, P and T, it is at high temperature and low pressure relative to the critical point of the air. So we assume this is ideal gas. And then what else? Okay, given in the question, the kinetic and potential energy change are zero. So these are your assumption that you need to write in the question. Obviously, you need to calculate and then write all the assumption used. So you need to write this assumption, right? So these are your assumption. Like I mentioned previously, you need to memorize all the only the general energy balance, and then you just remove all the insignificant term lah, right? And then now we're going to solve. So we know that this is for steady flow, the change over time of energy equal to 0. And then we know that for steady, your mass in equal to mass out, so which is equal to m lah, right? So this is the equation. Now you want to calculate your work in. So you need to find the properties of state 1 and state 2. So you need to find what? 2 and H1. What else? M is given in the equation. So you need to find the enthalpy in state 1 and state 2. Then only you can find what is your work input. So how going to get this value? You're going to use table A17, the ideal gas properties of air. So at enthalpy at this temperature, this is state 1, and then this is at state 2. You get values of enthalpy, and then state in the equation you get this is your work done for compressor. So easy, right? I think that's not very difficult. Okay, next. Okay, discussion. Note that mechanical energy input, because why mechanical? Because this require heat. It require work. Sorry, that's why it is a mechanical energy. So mechanical energy input manifests itself as a rise in enthalpy. Right, you can see there is a rise in enthalpy and heat loss from the compressor. So now work in is converted to what? Q out, and then and as a rise in enthalpy, right? So that's all for this example. Next. All right. So, as mentioned previously, for turbine, what's the important point for turbine that you need to remember? You need to memorize. For turbine, there is work out. Work is done because usually in turbine we use for electric generation. So you need to produce work, produce power. So that's you have work out. So where is general balance? Tak ada kat sini. So from the general balance energy, from the general energy balance equation, Q in plus W in plus M in of M1 H1 plus V square over 2 plus G Z 1 equal Q out plus W out plus M2 H2 V2. So you always start with this general equation. You cannot memorize for all engineering devices. So just start with this general energy balance equation. So you know that there is work out for turbine. Obviously, there is no work done. Work in, sorry. Okay. And then usually potential and kinetic energy is neglected, but then here you have the potential energy because in the equation is given. This is in the example. But later we're going to see the change in potential energy is very small. So that's why usually we neglect the change in potential energy. So you have Z. This is what? The elevation. So you obviously, because there is a change in elevation, so obviously your potential energy here is not equal to 0. This is according to this example lah, but usually turbine there is no the potential energy can be neglected, but then you need to double confirm with the question as well lah. That's why I ask you to write this general. Start with this first, then we're going to see what's the information given in the question. Okay, so this diagram here. This diagram here is the example in here. Okay, example 5.7. So the power output of an adiabatic steam is 5 megawatt. So work out is given now, and then the inlet and exit are indicated. You have a change in V and a change in Z. So obviously your potential energy and kinetic energy is not equal to 0. You need to calculate here is not equal zero, bukan zero. So you need to calculate here. Now compare the magnitude of delta H, delta KE, and delta potential energy. You need to compare the change in enthalpy, the change in kinetic energy, and the change in potential energy. Now you need to calculate this change. Now determine the work done per unit mass, meaning that you have this work, but then you need to calculate work done per unit mass. Now you want to calculate the small w, right? So small w is W, capital W, divide by mass lah, right? And then calculate the mass flow rate of the steam. Alright. Okay, now let's take a look at the solution. Obviously, you need to find what you have. You have the value of this one already, and then you need to find H lah. H. Okay, always start with this assumption. This is a steady flow, so a change in mass for control volume and the change of energy for this control volume equal to zero. And then what is given? Adiabatic. Okay, adiabatic meaning that no change in heat lah, right? So that's why you can remove this term because adiabatic. So the system is adiabatic, so there is no heat transfer. And then this is a turbine. Obviously, we have W out, so there is no work in. So your equation become MH plus, MH1 V. We left with this equation H2 plus, this is V1 Z1 V2 plus G Z2. So obviously you need to find the value of H1 and H2 because the rest is given in the equation. The rest are given in the equation. So you have V1, V2, Z1 and Z2. And then you also need to create the mass flow rate as well. So before that, you're going to find what's the value of H1 and H2 first. Okay, this one. So because steady flow operation, we know that mass in equal to mass out, and then there is work done by the system. Okay, so now you find what is H1. So at pressure equal to 2 MPa and temperature equal to 400 C, what's the value of H? Now the question is, where is the value of H that you need to refer to? Is it in saturated water table or superheated vapor table? So if you look at a P1 equal to 2 MPa, so if you open table A6, okay, can you open table A6? What is the value of T saturated? Can you check? Okay, so at P equal to 2 MPa, the saturated temperature is equal to 202.38. So you know your PV diagram like this. Something like this. So you know that here is desaturated. So here is compressed liquid. Here is mixture of saturated water and saturated liquid and saturated vapor. And here is this region is superheated vapor. So at T higher, okay, your T is 400, which is higher than T saturated here, saturation temperature. So what your steam is in what state? Obviously, if your T is higher than T saturated, it is in superheated vapor state. So that's why you need to refer to superheated vapor table. So when the superheated vapor table, and then add P equal to this and T equal to this, you find the value of H. That according to table A6, H equal to this. And then find H2. Okay. So H at state 2, you need to know what's your of your steam in state 2. In state 1, it is superheated vapor, because given that your T here is greater than the saturated or saturation temperature. Now what is your steam state in state number 2? Okay, given in the question, what's the information given in the question? So if you look in the question, you have this information. What is X? Your X is 0.9, meaning that the steam exists as saturated, a mixture of saturated liquid and vapor. Right, because X equal to saturated liquid, X equal to 1 is saturated vapor. So in between is you must have a mixture of saturated liquid and vapor. Right. Okay, so for state 2, we know that this is a saturated mixture of saturated liquid and vapor. So how's you going to calculate H2? So H2 is, you can calculate using this equation. H have X time HFG. So refer to saturated liquid table. So find the value of HF and HFG, and then you get your the value of H2. Okay. Now, once you get the value of H2 and H1, you can calculate the change in enthalpy minus the value, and then you get this is the change of your enthalpy, and then you also need to calculate the change of kinetic energy and potential energy. So the information already given in the equation. So substituting the value, you get this value of kinetic energy change and potential energy change. So what's the conclusion? Not yet. Okay. Next, what is the second question? You need to calculate work, right? So previously, you have this equation, right? So now you know your H, you know your V, you know your Z. So you know this all, and then you can, you don't know the mass yet. What's the second question? The second question determine the work done. Okay, you find what is the work done per unit mass first. Work done per unit mass. Given work done per unit mass, so you just divide by M. Yes, like this. Because just now you have this equation. So to find the work done per unit mass, you just divide the equation with M lah, right? So divide all with M. So you will get your small work out. So this is the value. So far, any question? Because you already have this information given, divide by mass. So there is no more mass here. This one also no more M. So you get this W out. Arranging the equation, you get your W out equal to this. Okay, now you can straight away calculate what is the mass flow rate by multiplying with W. By dividing the W, your capital W with the small w, because W out is M times W, small w. So now you can directly calculate your M by dividing W out with small w. So you get the value of mass. So any question? So that's why it's important to what? To memorize the memorize what? General energy balance. And then you need to know the principle uh, of the device. For example, if turbine, you know that in turbine you want to generate power, so there is work out principle of engineering device. And then the rest, what else? You need to know the change in your state, the change of state from 1 to 2. Then only you can find the value of your enthalpy. From these three values. Okay, first, the change in potential energy is insignificant in comparison to the change in enthalpy and kinetic energy. So this is typical for most engineering devices. So that's why usually, because the change is small, usually we neglect the change in potential energy. That's why we can just term in your general energy balance equation. And then second, as a result of low pressure and this high specific volume, the steam velocity at turbine exit can be very high. So, okay, this is very high because you compress it. So, meaning that you will have a high specific volume. So, your velocity should be very high. But then, the change, even though the velocity of state 2 is very high, you can see that the change in kinetic energy is a small fraction of the change in enthalpy, only 15.95 only compared to change in enthalpy. So less than 2%. So, and therefore often neglected. So usually the change in potential energy and kinetic energy can be neglected. So usually we assume potential and kinetic energy equal to zero because the value is so small, right? So that's the conclusion. Next, second device, not the second, the last week two, and then two, and then one, another one. So this is the fifth device, device kelima, valve. So what is throttling valve? Is a any kind of flow restricting device. You want to restrict the flow by adjusting the valve, right? So this restricting device will cause a significant pressure drop in the fluid. So this and sometimes we use a porous plug and capillary tube to restrict the flow. So usually used in refrigeration system or capillary tube. And then, okay, reduce pressure with no shaft work, little heat transfer, and relatively small change in energy. So this is the common assumption for throttling valve, right? So no work, no shaft work, and then little heat transfer and small change. So usually this kinetic energy change can be neglected, and then the pressure drop in the fluid is often accompanied by a large drop in temperature, and for that reason, throttling devices are commonly used in refrigeration and air conditioning. So you're going to learn about this later in next chapter. Next two chapter, I think. Okay, so never mind. You're going to see this throttling valve again in next chapter. So usually they are used in refrigeration devices and so always start with general energy balance for steady flow operation. So there is for throttling valve, usually there is no change in potential and kinetic energy. This is kinetic energy, this is potential energy, and then there is no heat no heat transfer. So you can remove the Q term, right? And then there is no work done or work produced in throttling devices, right? And then you only left with M H1 equal to M H2. So because M is M in equal to M out, so your equation is simplified to H1 equal to H2 and enthalpy 1 equal to enthalpy 2. So, okay, you know that enthalpy is U plus V or the internal energy plus flow energy. So they are constant because H1 equal to H2. Not constantly, not change lah, right? Now let's at throttling valve example. Now you have the refrigerant 1P4A enter the capillary tube of refrigerator. So capillary tube is a similar concept of throttling devices. So now given that this refrigerant and the saturated liquid at P equal to 0.8 and is throttled to a pressure of 0.12. So from 0.8 MPa to P2 is equal to 0. So as you can see, there is a significant pressure drop. So for restricting devices, there is a significant pressure drop. And then now you need to determine the quality of the refrigerant at the final state. What does it mean by quality? So you need to determine what? X. What's the value of X? The quality. So it enter as saturated liquid. So leaving with what? With what? Is it superheated or mixture? So you need to find. And then and temperature drop, determine the, okay, you need to determine one X and then you need to determine the temperature drop, which in temperature drop is C1 minus T2 lah. Right. During this process. You obviously do the first step you need to write the assumption. Transfer is negligible and then kinetic energy change is negligible. You can also write potential energy change is also negligible. So you know that for throttling process, the enthalpy of refrigerant usually constant. So H1 equal to H2. Right. So you need to find what is your H1 and what is okay. You need to find your H1 and then once you know your H1, your H2 is equal to H1. Then only you can find the X, the value of X. Right. Okay. Is the liquid. Find what is the value of H. So at P equal to 0.8, you know that this is the T is not given, right? T is not given. So you because saturated liquid, so your T1 obviously is the saturation temperature at this pressure. So T saturated is 31.31. This is from table A2. And then find the value of HF because this exists as saturated liquid. So your H1 is equal to HF at 0.8 MPa. So looking at the saturated liquid table, so you get this value of your HF and then for state 2, in state 2, you know that H1 equal to H2. So obviously H2 is equal to H1. And then you find what is HF and HG because you're going to find your value of X. So because you know that X is what? X is from this equation. This is from Dr. Nisa kan, right? So from this equation, you can calculate your X lah. So substituting the value of H2 which is equal to H1 and then this is HF that you find at state 2, and then divided by HFG. So you get the value of X, which is 0.3, meaning that this is a mixture, right? Saturated liquid vapor mixture.
So now you have solved the first question where you determine the value of x, and then the second question is what you change in temperature. Okay, so you know that because this is at state 2, the refrigerant exists as saturated mixture, meaning that
Median, tak dengar suara.
oh really? Wait, testing.
Alright.
So we have
So we
the
have
first
solved the
question,
first
right?
question.
But now you need
Alright, but now you need to
what is the
find
change
what
in
is the change in
temperature or
temperature or
temperature drop. So you
temperature
need to
drop. So you
find
need to find
what is
what is
T1 and then
T1
what is
and then what is
T2.
T2.
What is T2?
What is T2?
The value is not
The value is not
given, right?
given, right?
In the
In the
question,
question,
the value is
the
not
value is
given.
not
So you
given.
need to
So you
find
need
what
to
is
find what is
T1 and
T1 and
T2.
T2.
Okay.
Okay, so
So
because
at
at
state
state
1,
1,
it is
it
a
is a
saturated
saturated
liquid.
liquid.
Obviously, your
Obviously, your
T is
T is
equal
equal
to
to T saturated or saturation
temperature,
temperature, which is equal to this.
and then
And then
similarly
similarly,
for
for
two,
state 2, it
it exists
exists as
as
a
saturated
saturated
mixture as
mixture
well.
as well.
So
So
if you
if you
recall
recall
the
the
PV,
PV,
so this
so
is
this is
saturated
saturated
liquid,
liquid,
saturated
saturated
vapor. So
vapor. So
in
in
between
between
here
here
is
is
mixture
mixture
of
of
saturated
saturated
liquid and
liquid and
vapor.
vapor.
So
So
your T
your
is
T is
T
set,
saturated
saturated saturation
saturation temperature,
temperature,
saturated
saturated
temperature
temperature
at
at
P
P
equal
equal
to
to
this
this
at
at
state 2
state 2
and
and
P
P
equal
equal
to
to
0.8
0.8
at
at
state
state
1.
1.
So
So
you
you
find
find
the
the
saturation
saturation
temperature
temperature
at
at
state
state
1
1
and
and
state
state 2,
2,
that
that
is
is
your
T1
T1
and
and
T2.
T2 respectively.
So
So now you
now
can
calculate
calculate what
is
is
temperature
temperature
drop.
drop.
So
So change of T is T2 minus T1. So your T2 is this, and minus this, you get this value of your temperature drop.
Okay.
Okay,
Next.
next.
Okay,
Okay,
next
next
is
is
the
the
discussion.
discussion.
Okay, note
Okay,
that
note that
temperature of
temperature of
refrigerant
refrigerant
dropped by
dropped by
this
this
value,
value,
and
and
then you
then
know
you
that
know that
because
because
x
X
equal
equal
to
to
0.34
0.34, X2
x2
equal
equal
to
to
0.34,
0.34, meaning
meaning
that
that
34% of
34% of
the
the
refrigerant
refrigerant
vaporizes
vaporize
during
during
this
this
filtering
filtering
process,
process,
and
and
energy
energy
needed to
needed to
vaporize
vaporize
this
this
is
is
absorbed
absorbed
from
from
the
the
refrigerant
refrigerant
itself
itself
because
because
there
there
is
is
no
no
heat
heat
transfer.
transfer.
That's
That's
why
why that's why
you have
you
this
have
statement.
statement,
The
the
refrigerant
refrigerant
energy
energy
needed to
needed to
vaporize
vaporize
is
is
absorbed
absorbed
from
from
the
the
refrigerant
refrigerant
itself.
itself.
Any
Any
question?
question?
If no
If no
question, we're
question,
going
we're
to
going to
proceed
proceed
with
with
next
next
engineering
engineering
devices,
devices,
which
which
is
is
mixing
mixing
chamber.
chamber.
So,
So,
okay,
the
the section
section
where
where
the
the
mixing
mixing
process
process
takes
take
place
place
is
is
referred
referred
to
to
as
as
mixing
mixing
chamber.
chamber.
Mixing
Mixing
chamber
chamber
does not
does
have
not
to
have
be
to
a
be a
distinct
distinct
chamber.
chamber.
And
And all the
ordinary T
ordinary T
elbow
elbow
or
or
Y
Y
elbow in
elbow
a
in a
shower,
shower, for example,
serve
serve
as
as a
mixing
mixing
chamber for
chamber
the
for the
cold
cold
and
and
hot
hot
stream.
stream.
So,
So,
meaning that mixing
mixing
chamber
chamber is
doesn't
doesn't
have
have
to
to
be
be
a real
a real
distinct
distinct
chamber. You can see this,
chamber.
you know,
You
okay,
can see
look,
this,
this is
you know,
chamber
okay, you
for
look, this is chamber, you know, but
instead of
instead
a real
of a real
chamber itself,
a chamber
okay,
itself,
an
okay, an
ordinary
ordinary
T
this one
elbow
T elbow
height
height
ni
ni
T
T
elbow
elbow, this is
or
T elbow
Y
or
elbow
Y elbow or
joint
joint lah in your shower
is
is
served
served
as
as
mixing
mixing
because
because
they
they
mix
mix
between
between,
there
there
is
is a
a mixing
mixing
process
process
where they
where they
mix
mix
cold
cold
and
and
hot
hot
water.
water. Okay, the conservation of mass principle for a mixing chamber require that the sum of incoming mass flow rate equal to mass flow rate of. Okay, so this statement is like this. This is what it means. Mass flow rate in equal to mass flow rate out. So if you have two inlet here, two inlet, meaning that M1 plus M2 equal to M3. So this is inlet, this is outlet. So that this is what it means by this statement. And then the conservation of energy equation is similar to the analogous to the conservation of mass, meaning that sama jugalah energy in equal to energy out. Okay, so this is the mass balance. Like I wrote just now, you have two inlets and one outlet. So inlet equal to outlet, and then similarly for energy, you need to have three inlet. Sorry, you need two inlet and one outlet. That's why you have one M1, M2, and M3. H1, H2, and H3. And this equation is already simplified lah for you. But if you write the general energy balance, you have all the heat, work, and kinetic change in kinetic energy and potential energy. But for mixing chamber, usually they can be neglected, leaving the equation only equal to this early M and enthalpy. Right. So now let's take a look at example 5.9. Now you have the ordinary shower where you have hot water mixed with cold water at this is T1, this is T2. Okay, if it is desired that steady stream of warm water, meaning the outlet you want your outlet to be 45 degrees, so this is T3. Now you need to determine the ratio of mass flow rate of the hot to cold water. So this is hot stream. This is cold water. So you need to determine ratio of mass 1 divided by mass 2. You need to determine this ratio. You need to calculate this ratio here. Ratio of mass flow rate of hot to cold water, and then assume that the heat chamber negligible and mixing take place at pressure of 150 kPa. So usually first and foremost we need to write the assumption first. Obviously this is the first assumption. This is steady flow operation. Since there is no change with time at any point, there is no change in mass and energy of the system, of the control volume. And then this is second one, given in equation, kinetic and potential energy are also negligible, so they are equal to 0. And then there is no heat loss, so heat can be neglected. There is also no work interaction involved. Okay, so the equation only left with only mass flow rate and enthalpy values. Okay, we take the as a system. Okay, obviously this is a control volume since mass cross the system boundary, and then we have two inlet and one exit, just like I mentioned previously. And then under the stated assumption and observation, mass and energy balance can be expressed in the rate form as this one already mentioned just now, already discussed. So you have this equation. And you know that what is M3? M3 is equal to M1 plus M2. So you substitute it here. And then if you divide by mass of cold water, M2, so you will get the ratio that you need to calculate, the ratio of hot water over ratio of cold water. So your Y here is equal to M2 over M1 given M1 over M2. is the desired flow rate M1. Your hot water, you need to calculate the ratio of mass flow rate of hot over cold water, right? Just now I already right. M1 over M2. M1 over M2, ratio of hot over cold water. So M1 over M2. So you have this equation. Now what you need to find the value of enthalpy. H1, H2, and H3. And then M1, you also need to find M1 lah. But before we find M1, you need to find H1, H2, and H3 enthalpy of stream 1, stream 2, and stream 3. Alright, given that operating pressure is 150 kPa, so if you check the saturation temperature at this pressure, the saturation temperature is 111 and 0.35 degrees C. Okay, now since the temperature of all three streams, so this is the temperature of all the three streams is 60, 10, and 45. All of these temperature are below this value, meaning that the compressed liquid, the water in all three streams exists as compressed liquid. Ini given in the TV diagram. So okay, this pressure, the saturation temperature is 111. So below T saturated, so your water exists as compressed water. So the compressed water, you can just refer to the enthalpy of liquid at their respective temperature. So at 60, at 10, and at 45. So you need to determine, you need to find the value of HF, because we know that this is compressed liquid. So that's why it is important for you to know the current state of the water. Is it a saturated mixture? Is it a saturated? Is it a compressed? Is it superheated? So that's why it is important for you to know that, because you're going to extract what's the value of your enthalpy. Okay, and then what else? So now you have all the values of enthalpy. Now you can find the ratio of hot water to cold water. So it is equal to 2.33. So note that mass flow rate of hot water must be 2.33 times the mass flow rate of cold water for the mixture M3 to lift at 45. So we have solved the problem. So you need to only find the ratio of mass flow rate. Any question?
So that's
What
why
I highlight just now. I stress it just now. You need to memorize all the only the general energy balance equation, and then you need to know the working principle of the engineering devices, and then you need to also know the state of the change of state from state 1, state 2, state 3. You need to know the state lah. You need to know whether it is compressed liquid, whether it is saturated liquid, or mixture of saturated and vapor, or superheated. Then only you can solve this problem. Next, this is the most commonly used in chemical engineering course, heat exchanger. You're going to see heat exchanger, or to find the heat exchanger again during your energy, heat and mass course. And then what else? In most of the chemical engineering course, we will see exchanger. Exchanger. So heat exchanger are device where two moving fluid stream exchange heat without mixing or without contact. Okay, so now you have two stream. Okay, you have fluid A. For example, here you have fluid A and fluid B. fluid A, you want to heat it from
20 degrees C to
20 degrees
50.
C to
So this is
50. So this
cold
is
stream
cold
that
stream
requires
that
heating.
requires heating.
But and then you also have
And then you also have
fluid
this
B. So
fluid
the
B.
initial temperature
So the
is
initial temperature is
70 and then
70 and then
go to
go to
35. So this is
35. So this is
hot
hot
stream that
stream that
requires cooling.
requires cooling.
That
That
requires
require
cooling
cooling because we want to reduce the temperature. So now
the
the
heat
heat
from
from
fluid B
fluid B
can be
can be
transferred to
transferred to
fluid
fluid
A
A
that
that
requires
requires
heating.
heating.
So that
So that
is the
is the
basic
basic
principle
principle
of
of
heat
heat
exchanger where
where
you
you
change
change
the heat
the heat
between
between
two fluid
two fluid
without contact,
without contact,
without mixing.
without mixing.
Dia tak bersentuhan
Dia
pun.
tak bersentuhan pun.
But then,
But
they
then
can transfer
they
heat.
can transfer
Okay,
heat.
and then
Okay, and then
heat exchanger
heat
are widely
exchanger
used in
are widely
various
used in
designs. So
various
in
industries. They
various
came in
designs.
various designs. So
There are many
there are
types
many
of
types
heat
of heat
exchanger,
exchanger,
but
but
the
the working
working
principle
principle
is
is
to
the
change
to
the
exchange
to
heat
exchange
between
heat
two
between
streams,
two
between
streams, between
hot
hot
and cold
and
stream.
cold stream.
So
So
that
that
is
is
heat
heat
exchanger.
exchanger.
Okay,
Okay,
now
now
the
the
heat
heat
transfer
transfer
associated with
associated
a
with
heat
a heat
exchanger
exchanger
can
can
be
be
zero
zero
or
or
non-zero
non-zero
depending
depending
on
on
how
how
you
you
select
select
the
the
control
control
volume.
volume.
For
For
example,
example,
if
if
you
you
uh, select the
select the
control
control
volume to
volume to
be
be
the
the
entire
entire system, the entire heat exchanger, which
which
consists
consists
of
of
hot
hot
stream
stream
and
and
hot and
cold
cold
stream.
stream.
So
So
meaning
meaning
that
that
your
your
Q
Q
here
here
equal to
equal to
zero.
zero.
Because
Because
why?
why?
Because
Because
uh,
uh,
because
because
energy is
energy is
transferred
transferred
from
from
hot
hot
stream
stream
to
to
cold
cold
stream,
stream,
and then
and then
it
it
is
is
equal
equal
to
to
this
this
is
is
Q
Q
out
out
from
from
the
the
fluid
fluid
B,
B,
and
and
then
then
it is
it is
also
also
equal
equal
to
to
Q
Q
in
in
for
for
fluid
fluid
A.
A.
So
So
in
in, and they are in the system here, but there is no heat transfer
from the
from the
system to
system
the
to the
surrounding
surrounding
or
or
from
from
the
the
surrounding
surrounding
to the
to the
system.
system.
So
So
that's
that's
why
why
if
if
you
you
consider
consider
the
the
entire
entire
heat
heat
exchange
exchanger
as
as
your
your
system,
system,
there is
there is
no
no
heat
heat
transfer.
transfer.
Okay. And
Okay,
now if you
now if
select
you select
fluid A as
fluid
your
A
system,
as your system,
fluid A is what?
fluid A is what? Just now fluid
This
A,
fluid requires
that is fluid
heating, right? This is
requires
cold
heating, right? This
cold stream. So you
cold
only
stream.
select
So
fluid A
you
as your
only
system.
select fluid A as your
So this
system.
is your
So
system,
this
and then
is
what
your
is your
system, and
surrounding?
then
Your
what is
surrounding
your
is
surrounding? Your
fluid
surrounding
B. So
is
there is
fluid
heat
B. So there
transfer
is heat
from
transfer
fluid B to
from
fluid A.
fluid
So
B
that's
to
why
fluid A. So that's
your
why
Q is
your
not equal to
Q is
zero.
not equal to
Compared to
zero.
this,
Compared to
this is your
this,
system that
this is your
consists
system that
of
consists
fluid A
of
and fluid
fluid
B.
A and fluid
So
B.
the surrounding is
So the
outside
surrounding is
here. There
outside
is no
here. So there is no
heat
heat
transfer
transfer
to the system
to
of
system of
from
from
the
the
system
system
to
to
the
the
surrounding.
surrounding.
That's
That's
why
why
your
your
Q
Q
here is
here is
equal to
equal to
zero.
zero.
Any question?
Any question?
This is
This is
important.
important.
You need
You
to
need to
understand
understand
this.
this,
Or else
or
you can
else you can
answer the
answer the
question
question
on
on
heat
heat
exchanger.
exchanger.
So you
So
need
you
to
need to
determine,
determine.
so
So
if you
if you
determine
determine
fluid A
fluid A
ataupun
ataupun
or you
or you
determine
determine
fluid B
fluid
as
B
your
as your
system. This
system.
is
This is
fluid
fluid
B.
B.
Your
Your
the
the
system
system
is
is
fluid
fluid
B.
B.
If
If you
determine your
determine your
system to
system
be
to be
only
only
fluid
fluid
B,
B,
meaning that
meaning that
um,
um,
there is
there is
also heat
also heat
transfer
transfer
because
because
heat is
heat is
transferred.
transferred.
There is
There is
Q
Q
out
out
lah
lah
because
because heat
heat is
is
transferred
transferred
from
from
fluid
fluid
B
B
to
to
fluid
fluid
A. So
A. So
now
now
your
the
system
system
is
is
fluid
fluid
B.
B.
So the
So the
surrounding is
surrounding
your
is your
fluid A.
fluid A.
If
But
you
if you
select
select the fluid
A
A
as your
as your
system,
system,
the
the surrounding
surrounding
will
is
be
your
your
fluid
fluid
B. So
B. So
there
there
is
is
heat
heat
transfer.
transfer.
If
If
you
you
if
if
you
you
decide
decide
your
your
system
system
to
to
be
be
fluid
fluid
A
A
or
or
fluid
fluid
B.
B.
But
But
if you
if you
select your
select your
entire
entire
system,
system,
if
if
you
you
select your
select your
system to
system
be
to
the
be the
entire
entire
heat
heat
exchanger
exchanger
that
that
consists
consists
both
both
fluid
fluid
A and
and
fluid B.
fluid B,
So
so
the
the
surrounding
surrounding
is
is
outside
outside
here.
here.
As you
As you
can see,
can
there
see,
is
there is
no
no
heat
heat
transfer
transfer
because
because
this
this
is
is insulated,
insulated area lah,
lah,
right?
right?
So there
So
is
there is
no heat
no heat
transfer
transfer
from the
from the
system to the
system to the
surrounding. That's
surrounding.
why
That's why
your
your
Q equal
Q
to
equal
zero.
to zero.
Any question?
Any question?
Is that clear?
Is that clear?
If not clear, then you cannot.
If not clear, then you cannot solve the
problem.
problem for heat exchanger.
Any question?
Any question?
Right. If no
Tak clear, Madam.
Right, if no question,
tak clear, okay. I padam.
okay, tak apa, I padam balik.
Right.
Right.
Okay.
Um,
Given here the heat transfer.
Given here, the heat transfer is associated with,
your Q.
okay, your
Is
Q
zero.
can be zero
For heat exchanger and then
for heat exchanger, and then your
can
Q
be
can be
other than zero. Can be
other than zero, can be
20 kg.
20
Can
kg,
be
can be
anything other than
anything
zero.
other than zero. Okay, but this
To be
value
zero or non-zero.
to be zero or non-zero is
how you
how
select your
you
system.
select your system.
If you select your
If
system
you select your
to be
system
entire
to be
system,
entire system, which consists
fluid
of
A and fluid
fluid
B,
A and
you
fluid
know that
B,
the heat
you know
transfer
that the
only
heat
occurs
transfer only
inside here,
occurs
from
inside
fluid A
here,
to
from fluid
from
A to
fluid B to fluid
from
A.
fluid B to fluid
Right.
A.
So this is
Right.
the
So this is the heat
in the
transfer
system,
occurs
right?
in the
There
system,
is
but
no
there is
heat transfer
no
occurs
heat transfer occurs
from the
from the
system
system
or to the
or
system.
to the system.
So that's why your
So that's why
Q
your
equal
Q
to zero, no heat
equal to
transfer.
zero, no
And
heat
then
transfer.
if
And
you
then
select
if you select
only
only
fluid
fluid
A
A
to
to
be
be your
your system,
system,
meaning that
meaning
what is
that
the
what is
surrounding now?
surrounding
Your
now?
surrounding
Your surrounding
is
is
fluid B.
fluid B.
Right,
Right, as
you know,
you know,
for heat
for heat
exchanger,
exchanger,
in
in
this
this
case,
case,
the
the
heat
heat
is
is
transferred
transferred
from
from
fluid
fluid
B
B
to
to
fluid
fluid
A
A
to
to
your
your
system.
system.
So
So that's why your
Q
Q
is not
is not
equal to
equal
zero.
to zero. There must be Q equal to something else. Maybe 10, maybe 20. That is what I mean earlier. So you can also select fluid B as your system. So let's say you have okay, this is where the fluid B goes outside this pipe in the box. So if you select, let's choose the different color. Okay, if you select fluid B as your system, so this is your system, the purple one. The purple one. So your fluid A is not considered as your system. If you consider only fluid B as your system, meaning that fluid B is your system, fluid A is what is your surrounding, right? So for heat exchanger, heat is transferred from fluid B to fluid A. Ish.
So
So
from fluid B
from
to
fluid B
fluid A.
to
So there is
fluid A. So
Q
there is
out
Q out
from
from
there is heat loss
there is
from
heat
fluid
loss
A
from
to
fluid A to
from fluid B to
fluid
fluid
A.
A.
So meaning that your Q must be is not equal to zero. So it can be 10, it can be anything else. It can be 20, it can be 30 that but you need to calculate lah later. But this is just to show you that it is not equal to zero. If you select your system to be either fluid B or fluid A. But if you select your system to be all the entire heat exchanger that consists of fluid A and fluid B, so your Q is equal to zero because there is no heat transfer from the system to the surrounding or from the surrounding to the system. Okay, can you see the difference now? If you select the entire heat exchanger to be system, your Q equal to zero. But if you select either fluid A or fluid B as your system, then there is a significant amount of heat transfer. Any question? Okay, never mind. Let's take a look at the example. Okay, where is the example? Okay, this is the example. Okay, before that, okay, let's see the mass balance and energy balance first, right? Okay, now we know that M in equal to M out of the rate of mass mass flow rate is in equal to mass flow rate out. So now what is mass in for fluid A, for water? You have two fluid A, this is fluid A and this is fluid B, water and refrigerant. Right, for fluid A, what is in? You have,
this is okay. The
the number is given for you, 1, 2, 3, 4. So what is mass in
for water?
for water? Okay, for water, mass in equal to M1. So this is your M1. So your out is M2.
Okay,
For refrigerant,
what is
M in and what is M out?
This
This
is
is M in, M3, M3
equal
M4.
M3 is at the
M3 is at the inlet and
M4 is
M4 is the outlet,
and
right?
then
And then, okay, we can also express the energy balance. Okay, for heat exchanger, usually the kinetic energy, potential energy,
W all equal to
zero. Then Q is, the value of Q is
how you
depend
select
how you select your system. For example, you select your system to be the entire system that consists of
water and
water and refrigerant, meaning that your Q is equal to zero, just like I explained previously. And okay, so if there is no kinetic energy, potential energy, and work, your general energy balance become this equation. Only live with this expression, M1 H1 plus M3 H3. So what is M3 M and M1? This is in, this is out. Right, in equal to out. Energy in equal to energy out. So that's why M1H1 plus M3H3. So this is all the energy in, and then this is all the energy out.
M2
Is
out and 4
out.
is also
M4 is also the mass
Four,
out. For
this is
but this is for 2 is for water, and then 4 is for refrigerant. And then rearranging the equation, or you separate between water and refrigerant, and then you can also write this expression to be like this, right? Okay. Now, if you select your system
to be
only fluid
fluid
A,
your refrigerant.
your refrigerant,
So
so there is
the
heat transfer, where heat transfer to the
water,
water, right? Because you want to exchange the heat
refrigerant to water. So there is a loss
of Q,
which is equal to
which is equal to this, where Q in, QW in water,
heat
and heat
in
heat water in equal to Q loss of refrigerant. Heat gained by the water is equal to heat loss by the refrigerant, right? So you have this equation lah, where you have Q, the value of Q, and Q in for water is also equal to Q R out for refrigerant. So that's why you have Q in the energy as a balance expression. But if you select the heat exchanger to be your entire heat exchanger to be your system, there is no Q. That's why you only have the expression of M and H only, mass flow rate and enthalpy only, no Q. So that's why the expression depends the whether you select on how you select your system, either to select the whole heat transfer as your system, or just select only either fluid A or fluid B. Okay, now let's take a look at this example. Refrigerant
this
134A is to be cooled by water. So you have this refrigerant,
diagram
same
in the
diagram as in the previous slide.
you have
So you have
this refrigerant to be
this
cold,
refrigerant to
meaning that
be
this is
cool,
hot.
meaning that this is
From
hot.
hot,
From hot,
stream.
this is
So
hot
from
stream.
hot
So from hot,
to cold.
cold
So
lah.
this
So
require
this require cooling. This require cooling, but you have another stream, water, that requires heating because you want to increase the temperature. So you can increase the temperature of water by absorbing heat from refrigerant 134, which is your hot stream.
Okay.
Okay. Now, given that the refrigerant entered the condenser with a flow rate of 6, so this is what? Flow rate of refrigerant equal to 6 kg per minute at 1 MPa and 70. So this is P1 for refrigerant lah. P1 and T1 refrigerant, and leave at this is T2 for your refrigerant. Now the cooling water enters at 30 kPa and 15 and then leave at 25, neglecting any pressure drop. This means the mass flow rate of cooling water required and the heat transfer rate from the refrigerant. Okay, if heat transfer, obviously you cannot select the entire heat exchanger system to be the entire heat exchanger to be your system lah. You need to select either fluid, either water or refrigerant 134A to be your system. Then only you can find the heat transfer. But for mass flow rate, you can select the whole or the entire heat exchanger to be your system. Alright, so for first question, we select the entire heat exchanger to be a system. Then you write the energy balance, neglect all the insignificant term. So you only leave left with MH value, right? And then don't forget to write the assumption as well. This is steady flow, meaning that so there is no change in mass and energy. And then kinetic and potential energy change equal to 0, and then heat loss negligible, and then no work interaction involved. Okay, this is just the one that I have mentioned previously. Okay, this is the expression already mentioned to you, Millie. You have to write lah. Mass in equal to mass out. So what you need to write what is mass in and what is mass out. So mass in for water, M1, and then mass out for water is M2. So because this is steady flow operation, meaning that in equal to out. So M1 equal to M2 equal to the mass flow rate of water. And then similarly, you write the mass balance for refrigerant. So for refrigerant, in M is M3 and then out is M4. So in equal to out, which is equal to mass flow rate of refrigerant. And then write the energy balance, and then removing all the significant term, all insignificant terms, and then you can only have this expression for your energy balance. Alright, now this one also already discussed. You rearrange the equation. You put water to the left side and then another fluid to the left side, which is your refrigerant. Now you can determine what you can find the value of enthalpy for enthalpy 1 and enthalpy 2. So determine, and then next you need to determine the enthalpy of H4 and then enthalpy H3 in and out. So now we do it one by one. So now we do it for water first. So H1 and H2. Okay. What is the operating condition given? Given that T, you are given with T, and then you are given with P, if I'm not mistaken. Yes, you are given with P and T lah. This is P for P1 for water, and then this is P1 for refrigerant.
So now we're going to do
For water first, okay.
Okay,
At P equal to 300 kPa, you need to find what is the saturation temperature, because you're going to determine what is the state of your water first. So according to pressure equal to 300 kPa, according to your table, the saturation temperature is 133. And if you look at the temperature of water stream in and out, the temperature is 15 and 25, which is below the saturation temperature, meaning that your water is exists as what? As compressed liquid. Again, your TV diagram. So this is the saturation temperature. Okay, below the saturation temperature, your water exists as compressed liquid. So if compressed liquid, you can directly refer to the value of HF at 15 and HF at 25. So you get the value of H1 and H2. Now you do for refrigerant. Okay, for refrigerant, the pressure is what? Pressure is 1 MPa. Okay, the refrigerant enter. Okay, given in the question, enter the superheated vapor. Is it given or not? The question. Enter the condenser. Okay, not given. So you need to determine what is the state for your refrigerant. Okay, so at 1 MPa, what is the saturation temperature? Saturation. Yeah. What is the saturation temperature? Can you check at 1 MPa? Refrigerant. 1 MPa is 1000 kPa. So the temperature, okay, so T saturated at 1 MPa is refrigerant 39.37 degrees C. Meaning that if temperature is greater than saturation temperature, no, your temperature now is 70. This is your saturation temperature. This saturation. So here, at this state, it is what? It is a superheated vapor. So that's why you need to refer to superheated vapor, table A3, to find the value of H3. And then similarly for outlet, for refrigerant outlet, 4. P4 equal to 1 MPa, and P4 is 35. It's like this. This is 30 degrees C. Okay, at 1 MPa, the saturation temperature is 39. But now, the temperature is 35, meaning that it exists as compressed liquid. So you need to refer to the value of HF, enthalpy of a liquid at pressure of the enthalpy from table A11. So substituting all the values, you can find the mass flow rate of water, which is 29.1 kg per minute.
Any question? So that's why
Any question? That's why it is important to know the state of your fluid lah, whether it is saturated liquid, saturated vapor, mixture, compressed liquid, or superheated, because you're going to find the value of enthalpy. So
with this
information, we know which table we need to refer to. Right. So next, you need to determine the heat transfer. So if you want to determine the heat transfer, okay, you cannot consider the entire heat exchanger as a system. Instead, you need to select either refrigerant or water to be your system now in order to calculate the heat transfer. Okay, this is what is left after you remove all the insignificant term from the general energy balance equation.
Right. So now
Right. So now you already have this value calculated in the previous slide, which is 29.1,
right?
right?
And then
And then
this
this one
one
also already
obtained
obtained from the
table.
table.
Now
Now
substituting
substituting all the values into the equation, you can have this value of heat transfer. And bear in mind that Q in of water is equal to QR out, meaning that Q heat loss from the refrigerant is equal to heat gained by the water, because the heat is exchanged from refrigerant to water. So heat in for water is equal to heat loss from refrigerant.
Okay. Now
Okay,
discussion.
now discussion. Had we chosen the volume occupied by refrigerant as a control volume, we would have obtained the same result for QR out, since the heat gained by the water is equal to heat loss. Okay, meaning that
If you select
refrigerant as your control volume, as your system,
just now we
just now we
select
select
we select
we select
just now we select
just now we select
right.
liquid, right? Just now we select liquid.
We select
We select water as your control volume or as your system.
water.
Water.
And then
And then if you select refrigerant only as your system, you will also get the same amount of heat, because heat gained by the water is equal to the heat loss from the refrigerant.
Okay.
Okay,
That's all
that's all for heat transfer. Last but not least, we have pipe and duct. Okay, so for pipe and duct, okay, for pipe and duct, you need to consider all the terms in energy balance equation. Q in plus W in plus MH plus V plus
Z
Q out
plus W out
plus W out
and
plus
H2
M H2 plus V. This is V1, sorry now.
V2
Okay, this is V2
plus GZ2.
plus GZ2.
Okay.
Okay,
For
for
pipe
pipe or duct, okay, usually
only
only PE and KE are can be neglected. Then it depends on the question as well. Usually you in the pipe or duct you have all the Q and work as well, because you have, if you have electric devices here, you will have the work in as in the electric energy from the electric devices as your work in.
Okay, let's
Okay, let's take a look at one example for pipe and duct.
Okay, this is example
5.11.
Okay, the electric heater system
Use in many house consists of simple duct with resistant heater. Air is heated as it flow. So you have the Q, have the Q value, Q term, and then consider 15 kW electric heating system. Enter the heating section at this pressure and this temperature with a volume flow rate of 150. Now, if heat is lost from the air in the duct to the surrounding at the rate of 20 watt, determine the exit temperature. So you need to determine the exit temperature T2. T1 is given, and then given there is Q out, then there is W in 15. This is W in, and then this is 200. This is Q. So always start with the assumption. So this is a must-have assumption. Steady flow process. So it said there is no change in energy and mass of the control volume. And then okay, air given air is heated, right? Air. Air is heated. So air you assume to be an ideal gas because if you check the operating pressure and temperature, the temperature is high and the pressure is low relative to its critical value. So we assume it's ideal gas. Usually kinetic and potential energy are negligible. Or this is also not given in the equation. The value of there is no value of velocity and z. Right, in the question there is no velocity and elevation, so we assume there is no kinetic and potential energy change. And then constant specific heat, you can use constant specific heat at room temperature for air instead of using enthalpy. You can use CP, the value of CP. So now, start with the general energy balance equation. You remove all the insignificant term. You only have Q out. There is no Q in, so you remove. And then there is W in. There is no W out given in the equation. And then usually PE and KE is equal to 0 or can be neglected. It's only left with W in and MH term. W in, Q out, and MH term. Okay, now you know this is mass in equal to mass out, and then heat is lost, and then there is work in. Okay, and then at temperature accounted in heating and air conditioning. Okay, delta H can be replaced by Cp delta T. So instead of using delta H, you can use this value CPDT, where Cp equal to this value at room temperature. Okay, and solve here. Before that, you need now why? Okay, you need to find what you need to find exit temperature. But then you even with the value of mass flow rate, isn't it? You have all these value W in, Q out, and then H can be calculated by using CPDT. Temperature is there, but you don't know the T2, and then you don't have the value for of M. So you need to find the mass flow rate first. So okay, because this is ideal gas, you can use ideal gas relation to find the specific volume. Because why you find a specific volume value here? Because you want to calculate the flow rate. So you find what is specific volume of air first using ideal gas equation. You get this value. Next, you can find what is mass flow rate, which is this is volumetric flow rate divided by your ni lah tadi apa specific volume given, and then divide by 60. This is just to convert from minute to second. Next, substituting the known quantities. So you substitute all the known quantities. You already know your M, Q given in equation, W given in the equation, T1 given in the equation. Finally, you can find what is the value of T2. So that's why it's important to write the energy balance equation so that you know what are the unknowns and the known parameters so that you can easily solve the problem. Okay. Okay, note that heat loss from the duct reduce the exit temperature. So heat, because there is heat loss, you know that from heat loss, that's why you have a reduction in temperature from reduction from 7 no reduction. This is T2 is 21.9. So there is a increase in because there is Q loss to the surrounding. Any question? Ni bukan ni. This is increase.
Any question?
Okay, any question? So I think we have covered all. Next week we can proceed with a new topic, which is second law of thermodynamics, if I'm not mistaken. So I swear this part will come out in your final exam. The engineering devices, steady state engineering devices.
So you need to know all
So you
the
need to know all the
engineering devices
engineering devices
here in this
discussed
slide.
here in this slide.
I put
Yeah,
star
I
here,
put star here.
steady flow
Steady
of
flow of
engineering devices.
engineering devices. Energy
Energy
analysis of steady flow engineering devices. So I swear this will come out in your final exam. So make sure you
you know lah
how to solve this problem lah. And please memorize the general energy balance. This one general energy balance,
because they are not
because they are not given in the question in the appendix. You are only given with a steam table, and then please understand well the change in state lah, from saturated and then mixture and then superheated. So you know, if at this temperature which is greater than saturation temperature, what happen? What is the state of fluid? So you know, and then with this knowledge you can get the correct properties of whether enthalpy, internal energy, and whatnot. So if you don't know the change in state, then you cannot find the correct value of for your H. Okay. And then what else you need to know? You need to know the working principle of nozzle, diffuser, compressor. Okay, so let's summarize it here. So for nozzle,
you know that
so you want to increase the velocity, right? So velocity 2 is greater than velocity 1, but for diffuser it is reverse with nozzle, so V1 greater than V2. And then for turbine and compressor, so for turbine we know that there is work done or power generated by turbine, but for compressor you requires work, so that you have W in. And then throttling valve, you know that enthalpy is constant. Mixing chamber is what? Mixing chamber pun, I think your equation kinetic energy, potential energy semua is equal to 0, and then your equation left with only M and H, and then there is no work done, and then no Q lah, Q equal to 0. This is the common apa knowledge lah, but then also need to double confirm with the question as well. Sometimes they say there is a heat loss, so Q is not equal to 0. So it depends lah. And for heat exchanger, same kinetic energy, potential energy equal 0, and then no work done, and obviously there is heat lah, heat gain or heat loss from fluid 1 or fluid 2, from fluid 1 to fluid 2. Okay, but then 0. So only this also only leave you with H and Q lah, and Q. But then you need to separate between fluid A and mass balance. Okay, pipe end up usually you have Q, you have W. It depends on the question, but then usually PE and KE also equal to 0, right? So any question, make sure you know the working principle of.
And make sure you memorize all the
only the general energy balance equation. Okay. So with this we have finished 2 chapters, chapter 4 and chapter 5.
Any question?
Any question?
If no question,
If no question,
okay,
we can dismiss our class now. Thank you for your attention. Okay, before that, let me share you the attendance link. Where is the attendance link? Aish.
Okay,
Okay, tukar attendance ni. Okay, this one is your attendance. I forgot to change the date. Okay, this is your attendance link. Okay.
If no question,
If no question, we see you again to next week. Okay, next week. Same time, same link. So we'll start at 8:15. Okay.
Okay, thank you for your attention.
Okay, thank you for your attention.
Hi there.
Okay. All right.
Thank you. Bye. All right.
Okay, bye.
Okay, bye.
Thank you, madam.
Okay.
Thank you, madam.
Welcome.
Thank you, Doctor.
Welcome.
Thank you.
Welcome.
Welcome.